Okay, great. Welcome, everyone. Welcome to this Tripod seminar. Tripods is a NSF-funded data science institute based at Rutgers. This is also cross-listed as a computer science department, Rutgers Computer Science Department seminar. And also, I believe in the audience, maybe some of the critical AI group at Rutgers, which is an interdisciplinary group thinking about ethical issues in AI, including explainability. It's my pleasure to introduce Adnan Darwiche. We've known each other for quite some time. He does fantastic work. He is a professor at UCLA. He was the chair of the department at UCLA. He got his PhD at Stanford. He directs the automated reasoning group, and the group focuses on symbolic reasoning, probabilistic reasoning, and their applications to machine learning. Adnan has won many awards. I'll just name a few. He's fellow of the AAAI, which is the main society for artificial intelligence. He's fellow of the ACM, which is the main society for computer science. He was editor-in-chief of JAIR, one of the main journals in AI. He wrote a book on Bayesian networks, which I highly recommend. He's also recently posted on YouTube some tutorials on causality and causal reasoning, which I highly recommend you check out. He also has a position piece in CACM, which is really interesting. So in addition to his very strong technical work, he's been doing writing and talks to reach a broader audience, and really successfully, I think. So thank you, Adnan. Thank you for talking to us, and welcome, and I'll turn it over to you to talk to us about explaining decisions of AI systems.
Thank you, David. And again, thanks for the invitation to speak to this audience. All right, so this talk is actually about this picture, which is now dominating a lot of what's happening in AI in terms of practical applications. So we have some data typically labeled, learning process, we learn a box. ML system, typically a classifier. And what this system does is take instances and render decisions or labels them. And it could have different forms, a Bayesian network classifier, neural network classifier, random forest, and so on. And people are interested in knowing why it's behaving the way it's behaving. There are all kinds of questions that are popping up these days. They want to know, why was a decision made? Why was it not some other decision? Is it a robust decision? Was the decision biased, and so on? Typically, these are put under the label of explainable AI, or what has become known as XAI. I like more broadly to put them under reasoning about the behavior of the machine learning system. Now, the key observation that underlies the work that I'll be talking about, and that's relatively recent for me in the last few years, is the following observation. So even though this box is numeric in nature, and even though it was learned from data, quite often the instances are discrete, and almost always the decisions or the labels are discrete. So this thing really is just a fancy way of specifying a discrete function. So what we'll do is we will compile that box, and in particular, compile its input-output behavior into a symbolic representation, because the function is discrete, can be represented symbolically. And then we'll use that as the basis for our reasoning and for answering the kind of questions that you see on the left. And we will, in particular, represent this input-output behavior using circuits and tractable circuits, and I'll explain what that means later. But let's just take a concrete example to make this picture clearer. This is one of the simplest machine learning systems you can see, naive-based classifier. You have here three features. They're discrete, representing various tests. You have the class variable. You have all of these numbers. These are false positive negative rates, class prior. These get learned from data. And then the way you use this is you give me an instance which fixes the value of these. You compute the posterior probability on the class variable, you check against the threshold, and you render a decision, yes, no. Now again, numeric box learned from data, but the features are discrete. So the input is discrete, the output is discrete, yes, no. So this is really a decision function, a discrete function. And it's just a fancy way of learning and representing a discrete function. So in fact, in this particular case, you can represent the exact same classifier symbolically using this decision graph over these three features. So if you have an instance like this one, you just follow the edges in the usual way and you render the decision. No, now guaranteed for every possible instance, whether you do it this way on this side or whether you do it the traditional way by computing posterior checking against threshold, guaranteed you're going to reach the same exact decision. And this guarantee is done because of a compilation process that took this guy and generated that guy automatically with this particular guarantee. So now that you've done this, you really don't need this. You can take this to do the reasoning and to answer all kind of questions that we were talking about. Now, when you look at this, you see that this is an instance of a bigger game. The bigger game has three questions. First, what ML systems can be subjected to this paradigm, right? This is a very simple thing. It's a naive-based classifier, and we'll see that actually it's quite broad. The second question is, what symbolic representation are you mapping into or combining into? In this case, I'm showing a decision graph, but just one instance. We're going to use them quite often for reasons we're going to mention there, but actually, more generally, we're going to compile them into circuits. And in fact, you'll see that this decision diagram is nothing but a circuit. Now, why do we care about that? We care about what we map into because of the third question is, all of this is just to prepare us to do the analysis, to reason about behavior. So what are we going to do with these symbolic representations? And there are tough computational questions that have to be addressed. There's two sides to this third element of what can you do. There are queries we don't even know how to formulate, but when you formulate them, you have to compute them efficiently. So what symbolic representation we map into is critical to that. And we will map into what we would call tractable circuits because they will facilitate the reasoning and analysis part. So this talk is really about these three components. The bulk of it will be the last one. What can we do with the symbolic representation? But that's going to come in the second half. And in the first part, I'll start by talking about what symbolic representations and what ML systems and give you some insights there. Now, each one of these is a talk on its own, so we'll see how much we can do today. Let me start by making an observation. When we use decision graphs like here, which are familiar to people, people tend to get the wrong idea of what we're going to do with them. People like these, they can be learned directly from data. They think they're interpretable. That's not how we're using them. We're not going to visually inspect these things. In fact, these things can be in the millions, if hundreds of millions in terms of size, because they're being compiled, not learned. And I'll give you an example of that in just, so we're going to be subjecting them to automated reasoning techniques at the third part, right? And we don't care how big their size is because you're going to see what we compile into will be tractable. As long as we can store it, we're pretty much good. Just to give you some examples, I'm going to flash three benchmarks that we used from the literature, Bayesian network classifiers that we compiled and give you a sense of the sizes of the decision graphs that results from them. So this was an education network from some group in Europe. This was a diagnostic network from Microsoft Research classifiers. This is yet another example from Stanford Medical Informatics for diagnosing breast cancer. So all of these are Bayesian network classifiers. These are not naive-based classifiers. They are Bayesian network classifiers. This example was compiled into a decision graph that you see here. This is the whole thing, right? This is very difficult to analyze. Computing posteriors, checking against threshold. Here you see the whole thing, but this is considered to be very small. This is the exact thing without labels, right? It captures the whole logic that's happening behind this complex box there. But if you look more generally, you can see that the sizes can range from a few hundred to a few millions, at least for these benchmarks, right? And the sizes, of course, depend on what classifier you have, what threshold you're using. But my point is, we're not going to be looking at these things visually. We're going to be analyzing them automatically, as you'll see later in the talk. As long as we can store these symbolic representations because they're tractable, and I'll explain what that means, we're good. All right. So what I'll do next is first talk about that symbolic representation, the notion of a tractable circuit. This is a very foundational concept, and it's an area that's been going on for 20 years now, has matured quite significantly. I'm just gonna scratch the surface there and give you some of the key insights, I recently gave a 2-hour tutorial at the Simons Institute on the next 5 or 6 slides that I'm going to show you. So you can consult it. It's on YouTube. You can find it. And it says beyond NP with tractable circuits, because these are tractable not just for NP, but for things that are much higher and much more complex. But let me just start with the observation that I made earlier, that we think of these decision graphs as circuits, and you'll see that there's just one point in this space of tractable circuits. So if you look at a decision diagram like this one, you can think it's made of these ingredients, what we call decision nodes. You have a node, and in this case, we're assuming they're binary variables. If it's true, you go this way. If it's false, you go that way, right? So this is actually representing a Boolean function. For any values of x, y, z, if you follow the edges, you either land at a 1 or a 0, which is the value of the function at that particular instantiation of x, y, z. Now, when you look at a node like this, you can think of it as a circuit fragment. So what I'm doing here is I'm doing x is true and alpha, x is false and beta, and then I'm disjoining them. So we can think of this as just a circuit fragment. In fact, if you apply this transformation to the whole figure, you see you get a circuit, right? And this circuit happens to be what people call negation normal form circuit. It is negation normal form because the inputs are either constants, variables, or they're negations, and then layers of ands and ors. So it's only ands, ors, and negations can only appear next to variables. As you see here, you will not see an inverter or a negation inside the formula, right? So this is a negation normal form circuit. And because it came from this kind of creature, it ends up satisfying a whole bunch of properties. Decomposability, decision ordering. I'm going to explain a couple of these later, but due to these specific properties that this NNF circuit has, it ends up being tractable. And what does tractable mean? So the bigger picture is this. And again, this is a field that's been going on for at least 2 decades under either the name of tractable circuits or knowledge compilation. The idea is you have a circuit, it's negation normal form, as I said, variables or their negation, and then layers of ands and ors. Those are not interesting. And there's a whole bunch of properties that were identified over the last couple of decades. These are some examples, and I'm going to give you some intuition behind a couple of them. And as you put more properties on these circuits, the circuits start having names. So if you add decomposability to this circuit, you get something called DNNF circuits. You add determinism, you get this. You add more, you get the OBDDs we were looking at, and so on. And then people have been studying this. And by the way, I started this area with Pierre Marquis in this paper that won the H. Kaiser Prize at some point. What people have been doing is looking at 2 things. What happens when you start adding these properties to these circuits and getting these circuit types? 2 things happen. Tractability increases in the sense that a whole bunch of operations that are known to be difficult on circuits, they become tractable. And the second thing is the more properties you add succinctness, the sizes of these things start actually getting larger. So there is a whole space of these tractable circuits. Decision graphs is just one of them. In fact, happens to be one of the more tractable, but also least succinct. There are better representations in terms of size, and I'll expose you to a couple of them next. Very simple, very intuitive. So this whole area, as I said, is knowledge compilation. And just let's look at some of the operations here. So this is consistency or satisfiability. So if you just have decomposability and you get this circuit type, satisfiability becomes linear time on these circuits, feed-forward linear time, which is known to be NP-complete more generally. And model counting, which is how many satisfying assignments the circuit has. I just don't want to know whether it's satisfiable or not, but I want to count the number of circuit inputs that satisfy the circuit. That is actually sharp P. Counting class becomes linear if you have the first 2 properties and you get the circuit type and so on. So let me look at this from another
Sorry,
angle.
can I ask a question?
Go ahead.
Can you
Yes.
go back to the previous slide? I think
Yes.
yeah, this one I am a bit not sure. Like I don't understand the statement. Like how this becomes easy. Like what magic?
We're coming to it with concrete examples. All right.
Okay,
Let me roll
okay.
for a couple of more slides.
Okay, sure.
So let me first talk about this from a different angle. So you have these complexity classes. Everybody knows NP, PP is the counting class. These are bigger classes. Now it happens that all of these complexity classes, the prototypical problem for them are problems on Boolean formulas. You have a Boolean formula, we know what SAT is, that's NP. MASH SAT is the majority of assignments satisfying the formula. These are more involved. But the point is, all of these complexity classes, the prototypical problems are questions of Boolean formulas. We know now, for each one of these classes, we know of properties on NNF circuits and corresponding circuit type that allow you to solve the corresponding problem in linear time. Meaning, you want to do SAT, you get a DNNF circuit. If you manage to compile one, that is, if you manage to take this Boolean formula and convert it to a DNNF circuit, SAT in linear time. If you want to do MASH SAT, majority satisfying assignments, that's this class, you get this kind of a circuit, linear time. And I'll show you that now completely, and so on. So you can walk all the way to PP to the PP simply by getting your right circuit. So it's a methodology of computation. You want to solve problems, compile your Boolean formula into the circuit of the appropriate type and do it in linear time. If you look at
yeah, just make sure. I think I understand what you're trying to say. You're trying to say that after you have the circuit, you can run in the linear time of the circuit size. Is that exactly what you're saying?
Yes.
I see. Good. You're not claiming like, oh, good. You're not claiming like just suddenly this problem admits like very small circuits. No, the circuit is large, but you can run quickly. Good.
Exactly. And you can fail in the compilation. In fact, if you have something like probabilistic reasoning on Bayesian networks, there are 4 classical problems that people have been studying over the decades: MPE, MAR, MAP, and SDP. This is computing most likely state. This is computing marginal probabilities, all the way to computing expectations. These 4 are complete for these 4. And we have efficient reductions that can basically take any of these and convert it to a Boolean formula that if you then compile to the appropriate circuit, then you can solve these problems in linear time. These reductions are very efficient and practical, right? So this is a methodology for computation that's been happening for the last 2 decades. I've been heavily involved in this. Almost all of these circuit types were introduced by my group. And this looks like a theoretical exercise. It's not. This is a recent survey, empirical analysis by a group. Here they are. This is just last year. They went actually and evaluated 18 different systems for probabilistic reasoning, including some approximate ones. What I talked about is exact. And our system ACE, which is based on the picture I just showed you on the previous slide, ranked number 1. This was like almost 700 benchmarks from various things. So this is really not theory. This is in practice. You can download this. Actually, I found out that EPEG actually has been using this system and some of the underlying for quantum computing as well. Okay, I want to move on, but I really want to give you a couple of very concrete things so you see how elegant and powerful what's going on underneath. I wanted to expose you to 2 things: a couple of properties to see how simple they are, and a couple of feed-forward computations, like was asked earlier. Decomposability is the simplest of all properties, and if you have it, then you can do SAT in linear time. And it's very simple. If you have a circuit, a negation normal circuit like this one, it is a property about AND gates. So if you look at this AND gate, you look at the 2 subcircuits that are feeding into it. The variables here are LK and the variable here are PA. They do not overlap. So you need this for every AND gate. So think of it as you have alpha and beta. You want alpha and beta not to share variables. That's it. If your circuit is decomposable, we call it DNNF circuit, and now SAT in linear time. Right? You got NP. If you manage to enforce this property, you capture NP. You are basically taking the class NP and reducing it to a single property on circuits, which is decomposability. If you add another property called determinism, which I'll explain now, you get the next class PP. And then you can start doing MASH SAT, sharp SAT in linear time. And the new circuit type is called this. So what is determinism? Determinism applies to OR gates, and it's very simple. If you look at this OR gate, you look at the 3 inputs, call them alpha, beta, gamma. I want any pair of these to be mutually exclusive. So this and that can never be high at the same time. The first and the third can never be high. The second and the third can never be high. In this case, I'm evaluating this circuit where all of these variables are high. So high is red, this is blue. And if you can look at the circuit, no OR gate will have more than one input that is high. That's the property called determinism. If you have determinism and decomposability, you need another property called smoothness. Not important too. It's not hard to enforce. You can do counting now and solve sharp set in linear time. And let me show you how you can do it. It's the feed forward. You literally just assign zeros and ones to the input according to some process, and you multiply it and gates and add at OR gates, and you move upwards. That's it. And this is a circuit that has 16 possible inputs, and this number 9 is telling you that 9 of them satisfy the circuit. So now we managed to actually solve sharp SAT in a feed-forward algorithm on a circuit, as long as that circuit is deterministic and decomposable, between parentheses, smooth. So these reductions that I told you about, they take the problem, write the Boolean formula, convert it to a circuit of the right type, and then inference from there on is linear time. There is a more fancy version of sharp SAT where you give weights to the inputs of the circuit, and then you're counting, but you're not counting one for each satisfying input. You're adding a weight for it. That's known as weighted model counting. Same story. Instead of propagating ones and zeros, you start propagating actual weights of things, multiply and add, and so on. And hopefully, this gives you a sense of what's going on here. It's a very sophisticated theory. As you can see here, even though we had a Boolean circuit, we're now doing arithmetic operations. So there's another parallel world called tractable arithmetic circuits that I also introduced. I'm going to leave this a couple of high-level slides to go to the second part of the talk, but I recently wrote a book chapter on this subject. This just came out a couple of months ago. There was a book on neurosymbolic AI, and I had a chapter on tractable Boolean and arithmetic circuit. It is both editorial/survey. This is very recent. Even though we're going to be using these for explainable AI, people have been recently using these to regularize neural networks. They've used them, they've been basically incorporating them in machine learning pipelines, very different from what we're going to be talking about today, because they're also differentiable, You're going to see details in this chapter. Another recent tutorial I gave at PODS, the database theory conference, under this title, talks about the same thing, but from even broader perspective. So both of these are on the archive, and for this, there's a tutorial on my YouTube channel. I'll give you that later. Now, there are other properties, structured decomposability, partition determinism. We're not going to talk about that, and they lead to other circuit types. You can consult these videos or these write-ups, but the bottom line is you can hit E-MASH-SAT and MASH-SAT and reach PP to the PP all through this methodology. This is actually has been quite influential. You will see a whole bunch of titles like knowledge compilation meets database theory, communication complexity, knowledge compilation. Recently talked to EPAC from using it to quantum compile, quantum things. So I have a course on this subject on my YouTube channel. I'll give you a link to it if you want to go more in deep in these things, but let's just move on and get to the second part of the talk. So the summary here is we will compile these ML boxes into these kind of circuits that I showed you. Now, which circuit do you compile into depends on what do you want to do after you compile, what kind of questions you're interested in, all right? But most of what I'll be doing later, I'll be showing you examples from decision graphs in particular because they're pictorially easy to visualize. But our goal is not only to capture the input-output behavior, but in the form of a tractable circuit to facilitate number 3. What can we do with these? Now, what kind of ML systems? This is a subject on its own. The class that I just showed you have a couple of lectures dedicated to that, but I will just make a couple of general remarks and give you 2 main insights just to let you know, and then I want to go to the main part about the analysis. We've been mostly looking at Bayesian network classifiers, some very restricted types of neural networks, binary, and more recently decision trees and random forests. This is where we started. Most of our investment was here. In fact, the very first compilation algorithm was from 20 years ago, the one that compiled the naive-based classifiers into decision graphs. Nobody paid attention then because the community was thinking somewhere else. Now it's a hot area. More recently, we handled arbitrary Bayesian network classifiers, not just many base ones. As I said, these are binary neural networks. A lot of the work now we're doing is on decision trees and random forests. Again, there's a big community trying to do similar things, but not necessarily compiling into tractable circuits, just encoding symbolically without insisting that the encoding is tractable. Just quickly, in terms of conceptual difficulty, this is the easiest. And you'll see on the next slide why. Because the way decision trees and random forest learning works, they give you the problem. Even though there's numbers and so on, it's really underneath a symbolic representation, and you'll see why quickly. This is a little bit harder, but easier than this in the sense that here you're trying to capture input output, but the input output is very clear. It's a feed-forward process. In neural network, you have the input, you just walk the computation, you see the output. Okay, but in Bayesian networks, the hardest conceptually because when you have an observation and you compute a posterior probability to use to make a classification, the process of reasoning is very complex and you're trying to reverse engineer it. So if you look at the math involved and the theorems, this is the most complex because you're really reverse engineering a reasoning process. There is no reasoning here. There is no reasoning there. All right. And random forests and decision trees, they're easy to capture their behavior symbolically because they're already symbolic, even though if you have numbers, right? So look at this decision trees. This is a continuous number X, and this is a continuous number Y. But if you look carefully, the learning algorithm already found the thresholds. So I only care whether X belongs to one of these three intervals. Any number in this interval will be treated equally by this decision-making process. So I can view X as a discrete variable with 3 values, and I can view Y as a discrete variable with 2 values. And what this is doing is just specifying this discrete function, right? I didn't have to do any work. The learning algorithm already discretized things for me. So really capturing input-output behavior symbolically for these kind of systems is straightforward. I just want to do one more thing here before we go to the last part, which is tell you a hint about what's happened with Bayesian network compilation. Because in this framework, when you're doing the compilation of the input-output behavior, you'll have to use different techniques depending on what you're compiling. So if you're doing decision trees, random forest, that's one thing. If you're doing neural networks, that's another thing. If you're doing Bayesian networks, that's a third thing. But once you get the circuit from there on, it's all the same. It doesn't matter where you got the circuit from, okay? One of the main insights, or I'll just give you an example of the techniques we use to compile Bayesian network classifiers. How can I take something as complex as a Bayesian network and the inference behind it and give you a circuit back? And one of the main insights, I'll just expose you to one. If you look at this naive Bayes classifier that we looked at before, look at this prior. In this case, if I take this prior and drop it to this, the classifier does not change. I guarantee you, go and try every instance, you're gonna still get the same answer. And you can take this prior and move it all the way up to that. So as long as the prior is in this interval, the classifier does not change. And we were able to characterize these equivalence intervals and show the basically bounds of numbers that do not change the classifier. And then we, in this case, we compile these things by doing some kind of a depth first search in the space of features. And we use this notion of equivalence intervals to prune the search space. So that's why we end up being not exponential. And that's why we're able to compile these things. The math involved the theorems that allow you to infer these equivalence intervals is heavy duty Bayesian network inference and probabilistic reasoning. We're not going to get into this, but just gives you a sense of what goes on behind the scene for these things. All right, so we've been targeting all of these. Recently, as I said, we've been mostly looking at random forests, very large ones to scale that up. But I guess, let me see, with the time I have now, I want to go to the last part, which is, let's assume you took your classifier, whether it's one of these forms, you computed the circuit, what are you going to do after that? Because that's actually intriguing, not just from a computation point of view, but from a formulation point of view. And what we're going to do here is we're going to start small and expand, all right? And our starting point would be with the very first thing we did when we started this line of work, which is 2 years back, where we introduced the notion of a PI explanation of sufficient reason. This notion is very simple. It's very influential. It turned out to be. There's dozens of papers now on this subject. It's very simple. You give me a classifier. You pass it an instance, and the instance has 100 features, right? So there's 100, and the box says, I decided that. And you say, why did you decide that? So what we're going to do, we're going to look at the 100 features, and we're going to find a minimal subset. So let's say 100, I can isolate 7, and I say, these 7, that's why you made this decision. What does that mean? That means if you fix these 7 characteristics, you can vary the other 93 as you wish, and the decision will not change. So it's a minimal subset of the instance that guarantees that the decision will stick. We introduced this initially under the name of PI explanation. Recently, we've been calling it a sufficient reason, all right? Now, we'll start small, and then you see how it's going to mushroom into something very interesting. But let's take a simple example, and this example is intriguing, okay? We looked at this before. You got a patient, Susan, scanning test, blood test, urine, all positive. This guy classifies it as pregnant. And then you say, why did you conclude that Susan is pregnant? Now, what's the answer in this case? The sufficient reason is a minimal subset of the instance that guarantees a positive decision. In this case, it turns out to be scanning test came out positive, right? That's a minimal subset, the only minimal subset in this case of this that guarantees. Now, look at this guy. Look what happened here. This variable is not even involved in this path. People tell you decision graphs are interpretable. Not really, right? Try it at home. Fix scanning to positive and vary the other 2 as you wish, and walk down, and you're always going to land here. All right. So even on this tiny example, this result is surprising given to people's perception. But again, that's not the intention. Let me show you a little bit more involved example that would lead us to a notion that turns out to be quite big. In this example, all of the tests came out negative. So Sally tested negative for scanning blood and urine. And then the conclusion is she's not pregnant. And say, why? Now, in this case, I end up having 2 sufficient reasons, not just 1. The answer is because the scanning test was negative, and one of the blood and urine. So if you look, you'll see two sufficient reasons, 2 minimal subsets of this. Each one of them on its own is guarantees the decision. One of them scanning negative, blood negative, the other scanning negative, urine negative, and minimal. You cannot drop anything here. If you drop either this or that, you no longer have this guarantee. I wanted to bookmark a notion, which we're going to get to in just a little bit. If you take these sufficient reasons, all of them, and disjoin them, you get this formula. We're going to call this the complete reason. That is, every minimal subset of the instance that guarantees the decision, take them and disjoin them in one big formula. Let's call it a complete reason. That ends up being now a very big notion, as you'll see in a little bit. Let's bookmark it. But before we get to complete reasons, because we're going to use this to do all kinds of other things as far as reasoning about the decisions, let's just take a couple of concrete examples of sufficient reasons. This was a neural network on black and white images, 16 by 16, trying to tell 0 from 1. And so the features here are 256 pixels, right? 0 or 1. We gave it this instance, it says it's a 0. And then we say, why was it a 0? Why did you conclude this was a 0? One of the sufficient reasons was this, these 3 pixels, 3 white pixels. This means that for this neural network, any image that has these 3 pixels as white will be classified as 0, guaranteed. I'm guaranteeing you this now, including this one. Our graduate students were having fun with these things. So they created this to make sure that these 3 pixels are on. And I can guarantee you that it will be labeled as 0 by this neural network. Here's another example. This was a 1. And one of the sufficient reasons was this, and that I can tell you upfront that this neural network will classify this as a 1 as well. All right. So, as I said, this notion of a sufficient reason ended up being quite influential. There's like dozens of papers now since it appeared 4 years ago, and a lot of them are on the complexity of computing these things. Now, I'm going to get back to this notion of a complete reason, and you'll see why it's going to be the focus of the rest of the discussion. But I just want to tell you one thing about the semantics of these sufficient reasons, because they have very solid semantics, independent of complete reason, which we're going to talk about later, based on something that's known in computer science for decades, the notion of prime implicants. This has been studied for at least 50 years, and from the world of Boolean functions and circuits. So let me quickly review, because it's pretty important. Let's say I have a Boolean function. like this over 3 variables, the prime implicants of the Boolean function are minimal settings of the variable that guarantee that the function will trigger. So in this case, I have 3 variables A, B, C, and these are the 3 prime implicants. What does this mean? That means if you set A to true and B to true, this function will trigger. And that's a minimal subset. You cannot drop either A and B. And this is another way in which, a minimal way in which you can trigger the function. You set A to true and set C to true, and so on. So what is a sufficient reason? You give me an instance like this one, and you say A through B through C false. The function triggers, and you say why. So this is a positive. You say why. And it's sufficient reason effectively ends up being simply the prime implicants that are compatible with this instance. In this case, there's 2 of them. So 2 of these are compatible with this instance, this and that. So now you're saying, why did you decide that this is a positive instance? And I come back and tell you, because A was true and B was true. That's one reason. Another sufficient reason, minimal, is B is true and C is false. That's it. If you have a negative decision, you do the exact same thing, but you work with the complement of the function. So you have the complement of the function, you have the prime implicants of that, here they are. And why did you conclude that this is a negative instance? In this case, only one of these 3 is compatible with that, and it's this. So that's the sufficient reason in this case. That's the semantics, very clear, solid semantics. The problem is, and that's been known forever, that the prime implicants could be exponential. So when we started doing this, we would go and compute prime implicants and then filter out the ones that are compatible with the instance, until we discovered the notion of a complete reason. So our entry into complete reason was for computational considerations, but it turned out to be a much bigger story, as you will see, right? So just recall the complete reason. You take all of your sufficient reasons and disjoin them, and you get another formula, one formula only, that captures all of these sufficient reasons. This is how we thought about initially, and it was motivated computationally, but you'll see it's a creature on its own. In fact, you'll see that even though there is an exponential number of sufficient reasons in general, this could be quite compact. And whatever I want to do with these guys, sometimes I can do directly on this. So this is going to be now our center creature. We will get the complete reason behind the decision, and then we'll use it for all kinds of things, including bias and other kind of explanations, as you'll see in a second. And we will insist on representing that complete reason as a circuit, and particularly as a tractable circuit. So that's going to be the focus. So let me give you a concrete example that will explain this notion and show you what else we can do with it. Because as I said, at the center of this theory of explainability is going to be, get me the complete reason behind the decision, and we'll take it from there. This is another classifier for admitting students to college based on 4 features: SAT score, GPA, whether they had a good essay or whether they passed the interview. Remember, this is a decision graph, but it could have been compiled from a random forest or Bayesian network classifier and so on. So the sophistication of the analysis that you're going to see next applies to these numeric boxes. Okay. I have this, I got an instance. Here's an applicant. They scored this much on the SAT, they have this GPA, essay, interview, okay. They're rejected. Now I want to analyze, why was this decision made, blah, blah, blah. So the first step now is get me the complete reason. In this case, the complete reason is this circuit, this guy. We went through 3 different stages in computing the complete reason, even though the paper is only from 2 years ago. The latest one, which just appeared in AAAI a couple of months ago, showed a closed form for decision graphs. So if you have a decision graph, you have an instance and a decision on the instance, and you want to get the complete reason in linear time, you go through the circuit, one pass, I extract the complete reason, this guy. Now I'm ready to start playing and answering questions. You want to know the sufficient reasons, they end up being the prime implicants of the circuit. There's no filtering now. If you get the prime implicants of this, each one of them is guaranteed to be compatible with this instance. So I'm not generating the exponential ones to filter the ones I want, no. You compute the prime implicants of this guy, you got your sufficient reasons. Now, think of what is a sufficient reason. It's a subset of these characteristics that end up implying this and getting you the decision. A dual notion, which we called in this paper the necessary reasons, are prime implicates of this. Subsets of this, minimal, whose disjunction is implied by that. And those turn out to be very important, as I'll show you next. They allow you to answer a query how can I change the decision? And how can I change the instance in a minimal way to reverse the decision? Okay, let's take a concrete example. So first, another example of sufficient reasons. For this instance, this decision turns out you have two sufficient reasons. So this was rejected. And the sufficient reason, I'm telling you, look, as long as the essay fail and interview fail, I'm going to reject this person. Don't bother with these guys. You can do whatever you want with these. They will fail. They will be rejected as long as this is the case. This is another sufficient reason. If you fix the SAT score, GPA, and interview, I'm going to fail this person. Doesn't matter if they pass the essay or not, all right? These are the only sufficient reasons. In this case, they happen to be the prime implicants of that circuit I showed you. And remember, these are subset minimal. They're not the same length, right? This is 2 and this is 3, length 3. In this recent paper, we can also compute length minimal sufficient reasons to focus the explanations even more. If you have too many explanations and you're only interested in the shortest ones, we do that as well on the complete reason circuit. Now, let's look at the necessary reason. You can use this to say, what would it take to change the decision? This person was rejected. What would it take to get them accepted? And you get 3 necessary reasons. Each one of them is again a minimal subset of the instance, but with a different semantics. This says, if you change interview to pass, I guarantee this person will be admitted. Here's another way of doing it. If you reverse these 2 guys, then they will also be admitted. So what's happening here is we're finding minimal subsets of the instance that if you change, you guarantee a decision change. So someone was not given a loan. What can they do about their application to get the loan? And similarly, we can actually get length minimal necessary reasons. Now, this is a binary classifier in the sense that 2 classes. If you have multiple classes, then, and you are classified into 1 class, you can pick any other class and say, what would it take to be labeled that way? And you can pick specifically what you want to be labeled as, and this will work. You can see the paper does that. This notion, by the way, is also known as contrastive explanations and has been around actually for very long. Apparently, we were able to trace this to at least the 80s. And in the paper that I just mentioned that just came up in AAAI, there's at least a dozen references where people had variations on this guy. It started in cognitive science and philosophy. So it's pretty important notion of that contrastive explanations. Now, what else can you do? You get the complete reason, you get its prime implicants, you answer why question, you get its prime implicates, you get why not questions. You can do a lot more. And I'll just give you a couple of things here. One of them is decision counterfactual. Statements like this. Susan would still be admitted, even if she did not have a high GPA because she passed the entrance exam and comes from a rich hometown. Here you had a decision made and you're doing counterfactual reasoning about how would the decision be made and why. And in this paper, we introduced complete reasons. We showed how these statements can be evaluated based on the complete reason. So you have a classifier, you get the complete reason for a decision, and I can now answer questions like this. And surprisingly, bias. And this is a short story here. Let's first define what bias. What is a biased decision? Let's say you pick some of your features and declare them as protected. Let's say, ethnicity, gender, and so on. And we will say that the decision was biased. So you give me an instance, you make a decision on it. And I will ask you, is it biased or not? If I can reverse the decision, if I can change it by only taking the instance and only changing some of its protected features, nothing else. If I can make the decision change, then we will say that that decision was biased. All right, let's start with that. A theorem that we showed is that according to this notion of bias, a decision is biased if and only if each one of its sufficient reasons contain at least one protected feature. So you want to know whether a decision is biased or not? Enumerate its sufficient reasons. Check them one by one. If each one of them mentions a protected feature, I guarantee you the decision is biased, meaning I guarantee you that I can make it change by only changing protected features of the instance. That's interesting. But it turns out that if you have the complete reason, you can do the same test in linear time on the complete reason. If the complete reason is represented in an appropriate tractable circuit, you don't have to enumerate the exponentially sized sufficient reasons to do that. So You get the complete reason behind the decision. You can compute sufficient reasons. Why did you make the decision? You can compute necessary reasons. Why did you not make that? Or what would it take to make a different decision? You can evaluate counterfactual queries. You can check decision bias. That's pretty impressive. Very recently, with Pierre Marquis, who I started this area of tractable circuit with, we gave new semantics for complete reasons that are very abstract. I'm going to have a couple of slides on that next. It's pretty exciting because, as you see, it opened up the door even broader for doing further analysis. And I need just one concept here that shows you how we can do this in a very general way, which is the notion of a class formula. It's very interesting. So if you have a classifier like this, in this case is a decision graph. I have three classes, C1, C2, C3. And I have three features, X, Y, Z. Each one of these features have three values. So I have 29 instances in this case. What this classifier is really doing, or any other classifier, is just partitioning the instances into three groups, those labeled with C1, those labeled with C2, and those labeled with C3, right? And in this case, I can express or capture the instances in every class by a formula, a discrete formula. So I'm going to call them delta 1, delta 2, delta 3. We're going to call this the class formula. So if you look at this formula and you see what instances satisfy it, all of them will be labeled as delta as C1 by this guy. So I'm extracting these from this guy. So you can think of every classifier as simply a set of class formulas, right? It's a partitioning of the instances into classes according to the class or label. Good, simple. Now, let's say you have this classifier, three features, and let's say we have four classes, and these are the class formulas. And you give me an instance. You say, look, here's my instance. X took this value, Y took this value, Z. And then it was classified as C2. And you want to get the complete reason for this guy. All I need from you is the class formula for this class. And in this case, let's say it happens to be this guy. What is this? This is all instances that are labeled as C2, including this one. That's all I need. I need this guy and I need the instance. And then we introduce a logic operator called universal quantification, which you apply to this instance and this formula, and you get the complete reason. Let me show with a concrete example, and bear with me here. The complete reason for the decision C2 on instance is you do this universal operator, which I did not define yet, and you universally quantify the characteristic of the instance from the class formula. In this case, you're going to get this formula. That's the complete reason. It's a declarative, straightforward, as you see by definition, operation. And this is the complete reason. Let's try to read it. What does this say? The instance was classified as C2 because it had characteristic this and one of these two other guys. All right, that's the abstract aspect of this instance that made it get classified as C2. It's a very fundamental notion. The paper of this is a journal paper. It went directly to JER. It's 45 pages. It's really extensive because the semantics behind this operator is very rich. The paper just got accepted in the journal track of JER, of HCI. So there will be a small 4-page version of the 45 pages, which will go on the archive soon. Anybody who's interested in classification, I think should look at it because it not only gave us a declarative way of defining this influential notion of a complete reason, it ended up giving us something more like an SQL in database. In SQL, I give you a few operators, select, conjoin, do this and that, and people start composing them in different ways to do all kinds of queries. What this paper is doing is something similar using this and other Boolean operators. You can really compose now general explainable AI queries. So the definition of universal quantification is very simple as far as definition, but the paper talks about how to compute efficiently and so on. So I'm going to try to wrap up with a couple of more slides. What are we doing on time, David? 4 or 5 minutes is okay?
Yeah, 4 minutes and then little time for questions at the end. That'd be great.
Okay. So we now have a way to get these complete reasons in using only class formulas and this operator. Let me end with a couple of remarks. When we started this work, we started focusing on explanations, and then we expanded to doing robustness verification. We started with Bayesian networks and expanded to other types. We started with OBDDs and decision graphs and expanded to other types of circuits. So this is the bigger picture. I just want to have a couple of slides to give you a sense of robustness and verification quickly, and I'll end it. Robustness. You give me an instance like this, and it gets classified as 2. The way we define robustness as a number, which is how many features do you have to flip, or how many characteristics so that the decision changes. If you look at this instance, which was labeled as 2 by this neural network, its robustness is 13. What does that mean? That means even though you have 256 pixels, you have to flip at least 13 for the neural network to end up labeling this as something other than 2. If you flip 1, 2, 3, up to 12, it will not happen, regardless of which ones you flip. That is what is the robustness of an instance or a decision. Difficult in general to compute, but if your classifier is mapped into an OBDD circuit or that decision or the decision diagram, this can be done in linear time. You give me an instance, I can compute its robustness in linear time. That's an example. And then you can do classifier robustness, where you can average over all possible instances. And here is an example of classifier robustness. These were 2 neural networks, almost the same accuracy, very close. The average robustness of one of them was almost 12 and the other was 4. So very different behaviors when it comes to robustness. Maximum robustness here was 13 and this was 27. We even though you have 256 pixels, that's 2 to the power 256 instances. That's an astronomical number. But because we managed to compile these input-output behaviors into SDV circuits, we could do these plots, histograms, where for each one of them, on the x-axis you have robustness, and on the y-axis you have how many instances attain that robustness. And that's another way of showing you the comparison between the 2 classifiers from a robustness point of view. It's remarkable that you can do this. And the secret is not only because we managed to compile the input-output behavior of that neural network, but because we did it into a tractable circuit that facilitates this kind of computation, as we mentioned earlier. You can do other things like monotonicity. I'm not going to explain it, but this is something where people want to know, is the classifier monotonic or not? And if you manage to compile into OBDDs, you can check monotonicity in quadratic time. Monotonicity is just really concrete examples. Educational testing, you say Susan's correct answers include Jack's. So I expect that Susan would pass if Jack passed. In credit applications, Susan and Jack have the same characteristic, except Susan has a higher income. I expect Susan to be approved if Jack was approved. That's the intuitive way of saying, when do you expect monotonicity to hold? You learn these classifiers. For a particular application, you know they should be monotonic, but you don't know if they're monotonic or not. If you manage to compile their input-output behavior, particularly to tractable circuits, then you can do that efficiently. Final slide. The bigger picture here is we're now reasoning about what was learned. And we're doing it in a particular way by taking input-output behavior, capturing it symbolically, and going to the world of symbolic AI and CS methods, which are very rich. What I talked about is a specific way of doing this, which I call the compile then reason paradigm. We're doing this, but we're insisting that the input-output behavior is captured using the tractable circuit, because the theory of tractable circuits allow us to capture a very large span of queries. People do this without necessarily compiling into tractable circuits by going to SAT. They can scale better in some cases, but they have less access to queries because SAT is SAT, right? It's NP complete. But there is a broader picture than I plotted here if you do not insist on getting tractable circuits. So I'm done. I did mention quite a bit of things on my YouTube channel. You can just on YouTube type UCLA Automated Reasoning Group. You're going to hit the channel. You're going to find a lot of things there. And David, we can take it from here.
Great.
Thank you.
Yeah, thank you so much. Everyone's clapping over Zoom, which you can't hear. Great. Thank you, Adnan. Really, really nice talk. We have a few minutes for questions. And you can raise your hand, or you can just unmute and ask your question. Actually, Chen has raised his hand, so you can ask the first question.
I was clapping actually, but
Oh,
fine.
that was a clap. Okay.
Yeah, I do have a question, but like that's why I was clapping. So
Okay. Go
okay,
ahead.
thank you, Anna. So excellent talk. So yeah, so I probably like missed some thing you probably said it. I missed. So the reason for you to be able to, for example, that implication part, you can do it efficiently is because your decision tree has certain type of structure or something.
The which part? So is
Like
this
part, let's say like this part, how do you turn like how do you do this and turn it efficiently? You said that a closed form in polynomial time.
linear?
Yeah, okay.
Linear.
But
So the insight is the insight. And I have to tell you, this was really hard because it took us 3 iterations to get it, is to look at the decision graph as a tractable circuit. And when you look at it as a tractable circuit, and because of our new understanding of the complete reason being a quantification, universal quantification process, we then go and implicitly do the quantification. So this closed form implicitly is applying the quantification operator on the circuit that correspond to the decision graph. And we could only do this after the last paper with Pierre Marquis. Really fascinating.
Yeah. So
before that, we would take this and throw it to a whole bunch of pipelines, compiling code, do this, and now when we have this operator of universal quantification, everything became analytic, and boom, just really squeeze it out. But what's happening underneath is we are treating the decision graph as a tractable circuit, and we are doing universal quantification on it.
Good. Oh, I see. So decision graph. Okay, I see. I think my problem was that, so if every decision graph can be converted into a circuit, and then you have to have some magic because circuit is not like, not all the circuit can be efficiently converted to, yeah, but now, because in the first step, you already transform into tractable circuits.
Okay, let me tell you one thing quickly. For a decision graph, you can always get it into a circuit. For the circuit to be tractable, you have to have what people call the test once property. You cannot test a feature more than once on the path, except in the continuous case, you can do that, and the paper shows that. So in the continuous case, if you look at this, you will see that features are being tested more than once.
Good.
That works.
Good.
I think you're gonna love this paper, the AAAI 22, because it has all of these insights that you're going after.
Yeah, thank you. So also I have a okay, I'm gonna make this fast. Yeah, sorry for, or if time is up.
Let's see if there are other questions. Actually, I have a question. Oh, Dimitri, do you have a question?
Yeah, I have a question on Adnan, on your conversion of the decision tree from a probabilistic model. So if you have a probabilistic model and there are underlying distributions, there are many discretizations depending where you are, especially if it's a nonlinear problem. Especially you mentioned in medicine. In medicine, which I've been working 30 years, the biggest problem we have is we have partial data. You see, the measurements you get are not revealing of what the graph is. It's only a glimpse. That's why you have estimation theory, meaning I have impartial data, partial data, and I want to make a decision. That's how a doctor does. Sometimes the measurements we have are not complete. So you cannot make a graph easily. Because
that's about
medicine, for example.
I understand. I understand. That's a different story.
What I wanted to basically understand is what class of problems are you targeting? Those where your probabilities are very complete, and then you can do that.
That's very good. What is my input? My input is a learned system. I'm not getting into the business of learning. You learn something and you give it to me. I say, I learned this. I want to figure out why is it making the decision it's making. I take it from there.
Okay.
So if you cannot build a Bayesian network classifier to start with, then we're not going to play that game.
Yeah.
But maybe you can go to learn a random forest, then you give me the random forest, and then I try to play this game on it.
Yeah. Yeah, I mean, I'm more into the how to make the initial system to learn that.
Classify. But I'll tell
That's
you
why
one
I was
thing.
saying yeah.
But I'll tell you something, Dimitri.
Yeah.
Even though this is how it started, we have a collaboration going on with another university on learn systems in healthcare. They're learning random forests. And even though the idea was that we were going to help them explain, what happened is they ran our tools on what they learned, and then they decided that they're not happy with them. Even though the accuracy was good. They were like, what? It's doing this? And then they actually started redoing the learning part. And so it ended up being a tool that filtered into the design process. Now, we don't have any automated way of doing this, except in an anecdotal. But what happened there is they went and they relearned things and started doing all kinds of things, because this became a filter, in addition to accuracy of whether what they learned makes sense or not.
Yeah, I mean, for this class of system, we do continual learning, because there's no way you're going to learn with a class of data, because the biggest problem of neural nets, that's why they fail in these applications, real world applications, is because it's static. I mean, you assume a data set and then you want to apply it to the real world. They all fail. Autonomous driving is failing, this failing, all this stuff. So for this class, you need to be able to automatically adapt and do symbolic, but not symbolic way you describe, but more the way humans do symbolic. And it's a little bit different, but I just wanted to clarify more what you're doing. Makes sense, obviously, the way you do it. Okay. Well, thank you. Thanks a lot.
Adnan, so when you compile to one of these circuits, in the worst case, the circuit could be exponentially larger than the original. But so I'm just curious, like in practice, as you try these different networks, like how often does it just sort of explode, and how often does it fail where it just gets too big and it doesn't work? Or have you found that it's usually working?
I mean, you have now an expert in your department. I think both Iping and his visitor are doing this for quantum applications. So they have actual data they can share with you. But we do have some guarantees. For example, tree width, it's no worse than a lot of these things are no worse than exponential in tree width and other type of width parameters. So there is parametric complexity work. People have published many, many papers on characterizing the complexity of compilation by parameters of the underlying graphs. I don't know if there is specific patterns, but listen, this, I showed you this table. I mean, I was very pleased to see this. These are like 700, almost 700 Bayesian networks.
Interesting.
And our system A's take these networks and write a Boolean formula and compile it to a circuit with determinism and decomposability, on which you can do weighted model counting in linear time. And then it performs probabilistic inference using these weighted model counting. And look, I mean, you can, I mean, this stuff.
So this time includes the compilation time.
Oh, yes.
Yeah, okay, interesting. Cool.
I mean, this is, I mean, people have been doing dedicated algorithms for probabilistic reasoning for decades. Some of these algorithms are considered to be the core algorithms by some of the best groups in the world, and for a very long time. And this reduction-based techniques is just dominating.
I remember bucket elimination. That's Rena Dechter.
Right,
right?
and you've got belief propagation, generalized belief propagation, and some of these are approximate methods, not exact. ACE is exact.
Interesting.
The way, you will see in some of my writings, I basically, even though the term beyond NP is old, I basically popularized this recently, because what's happening here is just like you have the reduction-based paradigm dominate SAT, that if you have NP complete problems, you can either come up with a dedicated algorithm or you can reduce to SAT and run a SAT solver. This theory of tractable circuit is doing a similar thing, but beyond NP. So if you want to do a PP, NP to the PP, PP to the PP, that's today, and I challenge anyone, that's the best systematic way of doing it, is write out a formula, compile to a circuit of the appropriate type, and do it using feed-forward inference. And that's why people are loving this now, the feed-forward inference. They're integrating them with neural networks as either regularizers or to impose constraints on neural networks, because they're just feed-forward circuits, and you differentiate them. They just fit very nicely in the pipelines. That's another recent and common use.
Great. Can I ask you one kind of specific question on the go forward? It's like where you had the GPA was medium and you could transform it to either
Yes.
low or high. It was like a necessary reason. Yeah. Oh,
Yes.
keep going. Yeah, right here. The last one, like that was interesting because the GPA was medium, and then, but even going to GPA low would help.
No,
why is
okay.
that? Okay.
So I skipped a step.
Okay.
Necessary reason is a disjunction. You have to interpret this as a disjunction, okay?
Okay.
And it is implied. So what we know is this or that is implied. I have to break that. If the variables are binary, there's only one way to break it. So I can make this false, but okay. And here similarly, I can negate this, I get this. Now, because this, I have two. The necessary reason guarantees you that one of them will do it, at least one, but not necessarily all of them. So in this case, actually, this will indeed reverse the decision, this will not.
Oh, okay, okay.
So the necessary reason tells you, I guarantee you that if you negate these things or change them all, I guarantee you, in some way, I guarantee you can change the decision, but it doesn't pick one. But for binary variables, there is no other option. Excellent observation.
Okay, great. We're over time, but I'm happy to stay. But anyone who can stay, if you can, Adnan.
Of course.
Can we? Okay. Any more questions?
Yeah, one more question, Adnan, and maybe I don't have any other questions. Is you say GPA low, like, you know, I'm used to more to have distributions, like it's not low, right? What is low, right? Depends what high school you finished, for example, or what university, because low is relative, right? So, and then of course, if you try to make a circuit out of this, depending on how you define low, you can have multiple. That's where you have exposure to different types of. So how do you deal with issues like that, right?
Well, here it is.
Yeah.
The machine learning does it for us.
Yeah.
So what happens is, imagine that GPA was not discrete, was an actual number. And imagine you're learning a decision tree or a random forest. The learning algorithm finds the cutoff and defines it may not end up being just 3 categories, low, mid, and high. It may end up finding 5 different buckets for GPA. Machine learning does that. I'm getting the random forest or decision tree from you. I look at it and I see the thresholds that
you see
generate, and I discretize. And let me tell you something, because this is now my fascination. I'm in the middle of this now. What happens is, it gets nasty if you're doing random forest versus decision trees, because if you're doing decision trees and you do this, what I just told you, the discrete values end up being 4 values, 5 values. If you're doing random forests, every tree in the forest does its own cutoffs. When you combine 150 decision trees, you may get 10,000 discrete values per variable. The latest work that we've done is we can do all of this native on discrete variables. We used to binarize. So if you have a variable that has 5 values, we introduce 5 variables, Boolean variables, and it gets nasty. Now, in this latest paper, the AAAI, everything is done natively on discrete variables without going through Boolean logic. And I'm personally very interested in this for 2 reasons. It started with the random forest because I build these systems. And I was, in one case, I saw a variable with almost 100,000 discrete values. It's continuous.
Yes.
One variable. I'm not going to go generate 100,000 Boolean variables. So I can do it discretely. The other reason, which we delayed until recently, is quantized neural networks.
Okay.
And there, when you quantize and you're using 8 bits or 16 bits, you can go and really have Boolean variables for that. So this is something that we're aiming for next.
And I have one final question. This decision tree is based on categories I understand, like Iris, Virginica, whatever you have here. Well, in a neural net, of course, you have all this. If I give you a neural net, for example, and you want to convert it to something like this, there's going to be a lot of variables don't mean anything, right? So how do you create a symbolic? How do you convert your neural net?
As I said, for neural networks, so far we've only done binarized. So, you know, like you saw the images,
yes.
pixels. Okay, so you have the on-off pixels, and then the output is one of the digits, discrete. Now, for neural networks, even though you get continuous outputs, people always discretize, right? They get labels. So I'm not worried about that. What I'm worried about is when you have continuous inputs and the parameters, and that's why I mentioned quantized. Quantized is discrete.
Yeah.
But with very, very large cardinalities, not the kind of discrete people typically handle 10 and 12 values. You may end up having 2 to the 8, 2 to the 16 values.
Yeah. I mean, my issue with neural nets is they don't create any symbolic internal representation. You see, I force them sometimes with constraints or other methods, but otherwise you have the same problem where you're talking about the 0. They find from the data 3 pixels, so they haven't understood what 0 is about. And that's a fundamental problem they have, right?
Yes.
But there's an open problem in AI, okay? If I use a neural net, it's a great, optimization method, but how do I make sure it optimizes to the right categories that it's supposed to learn? And that's
I'll send you something. We did a toy thing where we took synthesized images of simple things like shapes like rectangles and 7 segment digits.
Yeah.
Why did we pick these toy ones? Because I can have an easy generative model for them using a Bayesian network.
Yeah.
And then we compiled the Bayesian network into a circuit and trained it using gradient descent, except that thing knows what a rectangle is, knows what a 7, and then we used convolutional network for the same task.
Yes.
It's embarrassing, the comparison. I mean, we did simple things like train on data with one noise, but test with data with a different noise, and the CNN collapsed. And what we had was sturdy, was unaffected, because it is looking for a rectangle.
Yeah.
It knows what it's looking at, so you cannot just confuse it by playing these simple tricks.
Yeah.
It was an extensive, the whole paper was just an empirical study like that. Anyways, I'm with you.
Sure. Anyway, these are nice open problems. I mean, the way I do it is I do NMF, non-negative mixed factorization, and I put them as constraints in neural net so that I push it to learn real categories.
What you wanted to learn.
Yeah, exactly. Yeah. Okay. Well, thank you very much. That was very nice.
So.
Interesting. And Fred,
Robert has his hand. Yeah.
Yes, Fred, go ahead.
Yeah, so very nice talk, Adnan.
Thank you.
Can we go back to the definition of robustness for a minute? So you talked about flipping. What if you have low, medium, and high? What does a flip there mean? Just a change?
Change.
And but now I can see some changes are bigger than others, right? If you change from low to high, that's a much more significant flip than low to medium.
Yeah, you will have to have a more refined version then. We didn't do that. So, but you can do that. You can actually, you can give weights for flips if you want. We haven't done it. This would be more like having sharp SAT versus weighted model counting. You can, so this is like based on Hamming distance, right? In fact, I do have a, where is it? Somewhere there, a slide. Okay, this is based on Hamming distance between two things. So you're just counting the number of changes, but you can define a more fine-grained notion of distance. Yeah, yes, I agree with you. Yeah.
Or kind of related to that, I mean, like a circle versus a smiley face, might have very few pixels flipped, but yet they are very different things. So kind of robustness doesn't capture that either, where just a few flips.
This particular notion, yes. I mean, it is one notion, It is based on having distance, and yes, it may actually not work sometimes.
But it may make sense to think about other metrics for the distance between two trees. And then you're really talking about how far away the new tree is from the old one.
But I think the message here is even this notion is hard. But it got facilitated when I managed to capture the input-output behavior using a tractable circuit. Because even decision robustness, it says here actually can't be complete. These are hard to compute, even these limited types.
Yeah, makes sense.
Great. Any more questions?
So I have a final question that is like not closely related to the topic, but did anybody like mention this can be related to like average case circular bounds? Like this question is a bit like computer scientist type, but I think it's probably a way to prove some function is not be able to get a knowledge graph or something, because so what you're saying is if you have a knowledge graph, then I can efficiently print a circuit such that it works, which I can verify. Now, if I want to prove some function is probably not learnable, I can do a contraposition and prove I cannot efficiently print a circuit for it. But I'm not sure. Yeah.
Yeah, I mean, again, you are questioning learnability to start with, and our starting point is you have it.
Okay.
Right? You have the classifier. If you have the classifier, then you have it.
Okay. No, I'm just thinking something like some potential connections to like impossibility results, but yeah, thank you.
Okay, great. Well, thank you again, Adnan. I really appreciate
Absolutely.
you coming here, giving us a talk. Really interesting, great talk. And thanks also for meeting with some faculty while you were here, while you were quote unquote here.
Absolutely. All right, very good. Thank you. Thank you, everyone.
Okay.
Thank you.
All
Bye.
right,
Thank you. Thank you. Bye. So